Hi, everybody. Welcome to section 4.2, the natural logarithm function. So the learning objectives for this section are to define natural logarithms, understand the relationship between logarithm form and exponential form, evaluate logarithms, convert back and forth between exponential form and logarithmic form, solve exponential equations, and use logarithms to solve exponential models. So let's go ahead and look at some definitions of natural logs and exponents. So logarithms and exponents are simply different ways of writing the same thing. So natural logarithm, the first form, so in the equation a equals e to t, the number t that when used as an exponent on the base e produces the number a that is called the natural logarithm of a. And the natural logarithm in the final form is that t equals the natural log of a if and only if a equals e to the t. Okay, so we're going to use our final form definition here to convert exponential and logarithm equations back and forth. So in this first example here, convert each exponential equation to this logarithmic equation. We're going to convert a equals e to the t to t equals natural log of a. Okay, so sometimes, just a quick note that a natural log will sometimes have a parentheses around its value. Sometimes it might not, just to keep that in mind. So if I want to convert y equals e to the 4x into a natural log, I'm just going to rearrange our variables. So what we would have here is 4x equals natural log of y. Okay, so our t goes there, and our a goes inside the natural log. Okay, same thing here. And our y goes inside the natural log. Okay, so let's go ahead and look at these next ones. So I want to rewrite this in the natural log. I'm going to have 2x minus 1 equals natural log of a. Likewise, this negative 0.2x equals a natural log of 25. Okay, I'm just rewriting it. I'm not solving for anything. I'm just rewriting it in terms of a natural log. So whatever in the exponent with for base e goes on the left-hand side, and then whatever is on the left-hand side goes into the natural log. Okay, so that's converting it to natural log. So what if we want to convert a natural log to an exponential form? So in this case, we are going from t equals natural log of a to our exponential form a equals e to the t. So for this first one, whatever's inside the natural log goes on the left-hand side, so 2x. And then whatever is on that right-hand side, sorry, the left-hand side goes into the exponent for e. So e to the 7. Okay, so likewise, this would be y plus 1 equals e to the y minus 5. And here we would have x minus 4 equals e to the 0.05. Okay, moving on to just evaluating some natural logs now. So for here, all we need to do is just compute these values. So what we would do is just use your calculator or use Desmos, whichever you see fit. But let's go to Desmos right now and calculate these values. So we have natural log. You can find the natural log button option in functions on the right-hand side here. scroll down to natural log, and then plug in those values. So we had natural log of 147, you get a value there, natural log of e to the 5th, and we get 5, and we get natural log of e to the 3.7, and we get a 3.7 as a result. So that's just us inputting into a calculator. So what we got was approximately 4.99. We had 5 and we had 3.7. Okay, so hopefully that's some practice with evaluating these natural logs with a calculator. So moving on to our next topic is solving these exponential equations. So because exponential and logarithmic functions are inverses of each other, they undo each other. We know that the following are true. So the natural log of e to the x will just equal x. And e to the natural log of x is just going to equal x. So notice above here, we had natural log of e to the 5, where x is our 5. So what did this equal? Well, we found that it equaled just 5. So that would be similar to the statement here, that natural log of e to the x is just going to equal x. And likewise in this situation with e to natural log of x just equals x. So we're going to use these to be able to solve for these exponential functions. Okay, so we have e to the x equals 65. So what I would need to do here, we know that logs and exponentials undo each other. So I'm going to take the natural log of both sides. That's typically the route with these examples. So let me rewrite our question here. E to the x equals 65. I'm going to take the natural log of both sides. So when that happens, the natural log and the e cancel out. So I'm left with x equals natural log of 65. And then this would just equal, if I put it in my calculator, I would end up with 4.174. Okay, so that's how you would solve one of these exponential equations. Why am I taking the natural log of both sides? Well, that's because I have this x stuck up top. I need to get this x down below on normal ground so that I can figure out its value. I can't figure out the x's value when it's stuck up top in this exponent. So I use the natural log to undo it, bring it back down with these principles here, and be able to get an actual numerical value. So let's go ahead and try another example. So I have e to the 2x minus 7. Same thing, I need to get this x out of this exponent, so I'm going to take the natural log of both sides. Okay, and once again, the natural log and e cancel out. So I'm left with 2x minus 7 equals natural log of 987. So I still need to get x by itself. So I just need to solve for x by moving everything over to the right side. So I'm going to add 7 to both sides. I will have 2x equals natural log of 987 plus 7. And lastly, divide by 2 to both sides. So what I would have is x equals natural log of 987 plus 7 over 2. So quick note, it's always just better to leave the natural log. You can calculate it right away, but you would just have a long decimal, won't be an approximate answer. So it's best to just save that calculation for the end. That way we can just input it into Desmos. So X would be approximately, let me just go to Desmos and calculate that. So we would have natural log of 987 plus 7. Let's put all this in parentheses. Divided by 2. And we get 6.9473. Okay, let's go ahead and write that in the notes. So I get 6.9473. And then that's my solution. Okay. Moving on to the next question. This question's a little different because we have this 6 multiplying that e to the x, right? So what's important here is I need e to 0.05 x by itself before I take the natural log of both sides. So in order to do that, I need to divide both sides by 6. So what I end up with is e to 0.05x equals 3. 18 divided by 6 is 3. Let me write this. Okay. And now I can take the natural log of both sides. So natural log e to the 0.05x equals natural log of 3. That cancels out. I'm left with 0.05x equals natural log of 3. I'm going to divide both sides by 0.05. And so what I'm end up with is x equals natural log of 3 divided by 0.05. And so that's approximately 21.972. And that's our answer. So here are 3 different cases of me solving for x when we have an exponential function. So now let's go ahead and look at an application problem of what we were just working on. So the growth function n of t equals 14 times e to the 0.019 t describes the growth of a county's bureaucracy and is the size in thousands of the bureaucracy. T is the time in years from 2000. Approximately how many years from 2000 will the size of this country's bureaucracy be? 20,500. Okay, so remember n is measured in thousands. So since n is measured in thousands, what I need to do is change this to n equals 20.5 since we're measured in thousands. So it'll be 1, 2, 3 moved over to 20.5. Okay, so that is my n. So what am I being asked for though? How many years? That means I need to find t. I need to find t. So what I would do is set up the equation as such. I would plug in 20.5, that's our n, into our output. So what I would have here is 20.5 equals 14 e to the 0.019 t, and solve for t. So much like our previous questions, I need to get t out of the exponent and have it equal to some type of value. So what I need to do here is divide both sides by 14. So 14 cancels out, and I don't get a exact answer for 20.5 divided by 14, so I'm going to leave it alone for now. But now what I need to do is take the natural log of both sides. Natural log and natural log. So what happens here is natural log and the base e cancel out, and what I'm left with is 0.019 t equals a natural log of 20.5. Let me rewrite that. 20.5 over 14. So now I'm going to divide both sides by 0.19. This cancels out, and I'm left with t equals natural log of 20.5 over 14 over 0.019. And so let's go to Desmos and calculate that. So Desmos is natural log of 20.5 divided by 14. And that's all divided by 0.019. And we get 20.072. Let's go back to the notes. And so we get t is approximately 20.072. So what does all this mean? That in approximately 20 years, from 2000, meaning the year 2020, the size of this country's bureaucracy will be 20,500. Okay, so that is how you use solving for exponents to figure out some type of variable in an application setting. But that's it for this material, and I'll see you next time. Thank you. Bye.